Now we're moving on to chapter 5, which is networking concepts. So for my folks who've done their ITF already, a lot of this stuff will be review, but it will dive a little bit deeper probably. Sections here, network components and types. That's 5.1, 5.2, network protocols, standards and services. 5.3, network devices, and then 5.4, network cables. You again, Abby.
You're welcome.
All right, router, wireless router, switch, access point. Old school modem still has that same pizza box shape with dots across the front. These are going to be your infrastructure or your intermediary devices, the devices that other devices connect to so they can talk. Your host devices are the devices that will act as like the endpoints on your network. In the net, using Cisco icons, will be your desktop computer. It looks like a desktop. Same thing for laptop. This tower-looking thing represents a server. This is a tablet, smartphone. This represents a printer, scanner, IP phone. So it's like a voice over IP phone, phones that connect to the network, and then cameras. And then for your transmission media, your communication pathways between devices through this networking equipment are going to be LAN cables. They'll look like a straight line. So that's what you have connecting devices inside of your network. Connecting to the outside world, like the internet, you'll have a WAN connection, and that'll look like a zigzag line, like a lightning bolt. If you have a wireless connection, you'll see these series of two wavy lines going, kind of weaving into each other. And then the cloud represents a cloud network, or it could represent the internet too. So now that we know what those icons mean, let's put them to use. Look at some of these network diagrams and the ways that we can lay out networks. So you can describe networks in a couple different ways, but the first way we're going to look at is describing a network in terms of geography. So how far or close together or far apart devices are in their network. The closest you can get, for as far as device geography in network topologies is a PAN, a personal area network. So that's a network set up between two devices that are within a couple hundred meters of each other. So think about Bluetooth. So if I have a Bluetooth I have a set of Bluetooth headphones, and then I got my smartphone, and I'm listening to music, I can put my phone on the table over here, and I can put on my headphones and sit over here, and I can still hear the music because they're in close enough range to communicate. But if I walk out of this room and walk upstairs, it'll start to break up because their range is limited. They have to be pretty close to each other within a couple hundred meters in order for that wireless signal to travel. So that's our closest range network, a personal area network. Next one up from that is a local area network. So that's like a network that's like the size of a room or maybe even a building, but still pretty close geographically. And that's going to be a wired network or sometimes even a wireless network, but it's in a limited geographic area. So again, like a building or a room. You have a virtual LAN, a virtual local area network that is physically it acts as if those devices are physically in the same place, but they can be spread out a little bit further than a local area network. But logically, inside of the circuitry or the configuration of the way that network works, those devices think they're grouped together close in a small geographic area. And then a wireless LAN, a wireless local area network, again, is a local area network geographically like we described before, but instead of having wired connections, it's going to use wireless connections in order to make that network. A wireless mesh network connects multiple wireless access points together to make the network bigger. So think about when you go to like a not a stadium maybe, or like a convention center, or some big building that has wireless in it, Home Depot, right? They don't just have one wireless access point in that building, because if they did, the range wouldn't be long enough. You'd walk from one side of the building to the other side and you lose wireless. So what they do to make it seem like it's one big wireless network is they'll have multiple wireless access points that can talk to each other, but they all share the same SSID or network name. So from a user's perspective, you think you're connecting to the same wireless network, but really you're connecting to one access point. But then when you move out of that access point's range, because they've been meshed together, they're working together, you will get a new access point will pick up your signal, and you'll seamlessly start communicating through that wireless access point instead of the one that you originally connected to. So that's another form of like geographic access network types. From there, we have our metropolitan area networks, or MANs. So that's a network that can span an entire city. A wide area network is our largest type of network, and that's a global spanning network. The biggest wide area network there is the internet itself. Those are networks connected to other networks connected to other networks. So basically a mesh network that covers the whole globe. A virtual private network isn't really like a physical network per se, a topology, but it's basically a method that allows a remote user or a remote site to connect to another site as if they're in the same geographic area, like almost like a LAN, but they use the insecure internet as their connection, but through a secure channel. So basically the VPN creates like a tunnel between the remote place and the LAN that you're trying to connect to, and it'll create this secure encrypted tunnel across the internet. So even though it's going across the insecure internet, because the tunnel itself is secure, if anybody tries to grab the data from out of it, they'll grab encrypted data and they won't be able to interpret it. The benefit for your remote user, is the VPN tricks their computer into thinking that it's on the local area network. So it gets to use all the same resources as somebody who's physically in the building. Printer access to servers, access to network shares, all of that stuff is able to be taken advantage of by the remote user, because from their computer's perspective, they're on the local area network. So this is a brief history of connectivity. I'm talking about some of the ways that we've been able to connect to the wide area network. All started off with dial-up internet. So that's internet that used the public switch telephone network, or sometimes called the POTS, plain old telephone service. They used the telephone wires as a way to transmit data, not just voice data information, but also data information. It's analog, it's slow, so they had to come out with something better. They came out with what's called ISDN, Integrated Service Digital Network. So this provided not analog, but digital signals that could go over a wire, and it could carry voice, video, and data. It was a little bit faster, and you had a dedicated line. With ISDN, you can get a dedicated line to provide those communications, but even that was still slow compared to what we have now, which is broadband. A broadband can be delivered in a bunch of different ways, but its main benefit is it has a higher bandwidth, which means it makes your network connection faster. These are our three types of broadband that are currently available. You got DSL, or digital subscriber line. This still uses the phone lines in order to transmit information, which makes it accessible to people because the phone lines run across the whole country, across the world. You know, different countries have their own phone companies, but you get what I'm saying? They're at least across the whole country, there's telephone wires pretty much everywhere. There's a pre-existing network. So DSL leverages that, but unlike dial-up, it has faster speeds because a special modem, if you will, called a DSL modem, increases the frequency, which increases the speed of the data transmitting through that wire, those telephone wires, as you're communicating over the internet. So you get again a speed boost when compared to wire to dial-up, but nowhere near what you see with the other two, cable and fiber. Cable uses another pre-existing network for data communication, and that's the cable television network. So with cable modem, with cable internet, you're sending your data signals across the same wires that your cable television traditionally travels over. So benefit of that is it's using a different type of wiring. It's not using the telephone wiring. It's using the coaxial cable wires that are running all over the place in order to transmit data. But it has some downsides though too. All of those cable wires eventually come together in what they call a trunk. So what that means is that eventually everybody in your area, all their data signals go to the same place, go into the same wire, which means that the more people there are online, the slower your overall network connection gets because everybody's data is going through the same wire eventually. But you do get still, even with that, the speeds are way faster than DSL. So that's like your Comcast, right? Then fiber. Fiber is the fastest of the three, but it's the one that you're not going to find everywhere. Most companies, at least on their end, have fiber, but the really good companies try to get the fiber as close to your home as possible. Because the closer they get the fiber wire to your home, the quicker you're able to take advantage of those speeds. And what makes fiber special is that it doesn't use electricity to send its data signals. It uses light. So basically, your data is moving at the speed of light. So the quicker I can get it moving at the speed of light, the faster my data transmissions are. Most places don't have fiber all the way to the home yet, but a lot of them have fiber somewhere along the line. So you're able to take advantage of those speeds at some point. Verizon is an example of a company that uses fiber in its for its network connectivity. Another type of internet service is line of sight, wireless. So radio signals have long been used for doing communication, wireless communication, like through the radio. But now they're using those same radio waves to provide internet signals. So with a line of sight wireless internet connection, you have to have a clear line of sight between the receiver, the thing that's producing a radio signal, and the thing that's receiving a radio signal. If anything blocks that path, or if you had like bad weather or something like that, then that will interrupt the signal. That's one of the reasons why satellite, which is another form of internet, satellite internet is kind of spotty because not only is it trying to not satellite internet, but yes, not satellite, antenna internet. So they have internet that can be projected, or wireless signals that can be projected from one antenna to another antenna. Those can be disrupted if there's a stormy day or if there's a tree branch in the way because it breaks the line of sight. I'm skipping ahead to satellite. Satellite, again, similar to our line of sight, it's sending a wireless signal, a radio signal, off to a remote receiver. In this case, it's going to be an actual satellite, so that it can then bounce that signal to another satellite. So you can see what's going on in the picture here. I have a satellite modem at my location. I use the satellite to beam that signal up I use a satellite dish to beam that signal up to a satellite in space, and then that satellite relays that signal to another satellite dish at the location where I'm trying to communicate with, or at least to my ISP, my internet service provider, so that they can continue relaying my message. This comes in handy if you're in remote areas where there happen to be no telephone wires or cable or what have you, but it's really slow. So if you have anything that's like needs to be in almost real time, they mention here like online games or voice over IP or video conferencing, none of that stuff will work on satellite because the signal's not fast enough. But if you don't have any other options, because you're in such a remote location, satellite might be the only thing that you could take advantage of. There's also cellular, so you can get to the internet through your cell phone now, using a cellular network, and the cellular network sends its radio signals to a series of cell towers, which then eventually can relay that radio signal to some type of service provider on the cellular side. So a lot of different ways to connect to the network. And then you can even share that cellular network. If your device has the capability, you can share that cellular network with devices that typically don't have mobile connectivity. So for example, let's say I have a laptop that can only do a wired network connection or do Wi-Fi, but I have a smartphone that can act as a hotspot or does what they call tethering. With that feature, I can basically convert my smartphone from a simple receiver and transmitter of mobile wireless signals to basically turn it into a wireless access point. And once I enable that feature to turn my phone into a wireless access point, now it allows other devices that typically only use Wi-Fi, they can now connect into my phone and use my phone as their wireless router. But those signals eventually still connect to the cellular network, because that's the way that phone is now getting onto the wireless, getting onto the internet, is via the cell towers. Next section, 5.2, networking protocol standards and services. So when we're thinking about protocols, one of the tools that we use to help organize them are these different networking models. There's two networking models that are really, frequently used. One of them is called the OSI model. It's a 7-layer model, but here we're using the other popular model, which is called the TCP/IP model, which is a 4-layer. It's a little bit easier to remember, especially when you're dealing with things from a networking perspective. So in the 4-layer TCP/IP model, we go from bottom to top. The bottom layer is the network access layer, and this is the layer that defines like the physical components of a network, like the types of wires that they use and the type of hardware, stuff like that. Then we have at the second layer, the internet layer. This is where we define the logical aspects of a network, like how it's addressed. That's why we have IP existing at that internet layer, that internet protocol, IP addressing and stuff like that. At the third layer, we have the transport layer. Transport is dealing with how data is moving from one system to another system. It's two different transport layer protocols, TCP and UDP, and we'll talk about those in a second. But these are your two options for moving data from one system to another system, or from one network to another network. And then at the top layer, we have the application layer, and we have a bunch of application layer protocols. The application layer has the most protocols, but these aren't actual applications like the type you install on your computer. Here is referring to the rules that those pieces of software you install on your computer use in order to communicate on a network. So, for example, there's a protocol called HTTP, Hypertext Transfer Protocol. It's the set of rules for how web pages are displayed. Google Chrome is a program that uses the HTTP protocol, but so is Firefox. It also uses HTTP, and so does Microsoft Edge. They're all user programs, but they use the application layer protocol, HTTP, to dictate or control how they display web pages to you when you use their programs. So that's kind of the connection between these application layer protocols and the actual applications that we use. But to jump back down to transport layer, TCP versus UDP. Again, transport layer protocols control how data moves across and around your network. TCP is what we refer to as connection oriented, and UDP is what we refer to as connectionless. The reason we refer to, I'll start with UDP, as connectionless is because it doesn't attempt to set up a reliable connection with whatever device it's trying to transmit to. Its goal is to get that data there as fast as possible, with as low overhead as possible. So it's not going to ask who's on the other end. It's not even going to acknowledge that the data is getting to where it's supposed to get to. It's just going to shoot it. It's going to get it, and it's going to send it as fast as it can. So speed is the main reason we want to use UDP. So two of the implementations they say UDP is useful for are for IP telephony and streaming video, streaming live video. The reason is, with both of those, with voice data and video data, you're getting so many data packets so fast that if you lose one here or there, you probably won't, as a human, you probably won't even notice. So you can stand to lose a couple of data packets without it being noticeable, as long as the majority of them get there. Versus TCP, which is our connection-oriented protocol. This one sets up a reliable connection before it actually starts transmitting data. A reliable connection means that it goes through the process of making sure that that device is on the other end, and it sets up a session with it before it starts transmitting data. That setup process is referred to as a three-way handshake. So basically, it's like TCP has manners. It says, "Hey, how are you doing? I want to communicate with you." The device on the other end says, "Hey, my name is whatever. I want to communicate with you too." And then the device that's trying to transmit again says, "All right, let's start communicating." And then it starts sending its data. Whereas UDP just steps in the room and starts talking. Doesn't know you from Adam. It's just sending data to you. So reliability is TCP's biggest benefit. And these are the three basic operations of reliability. It tracks and numbers all of the data segments it sends. So when data travels across the network, similar to when data is stored on your hard drive, it's not stored in one big chunk. It's broken up into smaller chunks so that it can send them faster. So that email that you sent isn't just one big email. It was broken up into multiple packets and sent one bit at a time, one packet at a time. Those packets, when they get to the other side, they have to be reassembled so they can deliver to you the thing that you asked for. So in order to make sure that they're being reassembled in the correct order, they need to be numbered. And also, in order to make sure that none of them got lost, they need to be numbered too. That helps with tracking. TCP also acknowledges that data gets received. So when it sends that packet, it doesn't send it out into the void. It waits for a response back from that receiving device to say, I got that one, before it sends the next one. I got that one. And it keeps going with that process. And then retransmitting unacknowledged data after a period of time. So it'll send, the TCP will send a packet. Again, it's waiting for the I got that one. That's they call it an acknowledgement. But if it never gets the acknowledgement, it waits a certain amount of time. They call it a TTL, time to live. Every packet has a time to live. After that time to live expires, then TCP said, it must have got lost. Let me send it again. And that's, again, why TCP is considered to be reliable. UDP does none of that. It just throws the data out there, and if it gets there, it gets there. Besides TCP and UDP, there are a lot of other protocols out there. These are some of the well-known ones that you should be familiar with. And then what their associated port numbers are. For every one of these application layer protocols, they have to use either TCP or UDP or both. Look at the layout. Application layer protocols connect to TCP or UDP or even both. They all connect to IP because they have to have an IP address to communicate on the wide area network. And then IP connects to either a LAN connection or a WAN connection, a local area or wide area network connection. So looking at this chart, we see how that's reflected. You got an application layer protocol, and then you can see if it uses TCP or UDP or both. But in addition to that, there's also a port number. So just to make it easier for your computer to know what protocol it's dealing with, every one of these application protocols is also assigned a port number to represent it. So DNS, our domain name services protocol, that does name translation. It converts human readable names to IP addresses and maps them together so that we as humans don't have to remember 72.138.5.6. All we have to remember is google.com. And DNS will handle the translation. Well, that DNS can use TCP or UDP as its transport layer protocol, so it can go fast or it can be reliable, and it's going to use port 53 as the port number to represent DNS. HTTP, I explained that one already. Let's see the web pages. It uses TCP, and its port number is 80. The secure version of HTTP for when you're transmitting sensitive data like bank information is HTTPS, HTTP secure. That can use TCP or UDP, and it uses port 443. So those are my web protocols. Then for my email, I can use SMTP, Simple Mail Transfer Protocol. That's my server email protocol for actually sending emails from clients to a server. And that uses TCP on port 25. POP3 and IMAP, those are two of my mail protocols that'll run on my email client, like on my computer, in order to pull emails from the server. POP3 will be for email client that's installed on your computer. IMAP is for like a internet-based internet-based email client, like a Gmail or something like that. Those POP3 they both use TCP, IMAP, and POP3. And POP3's well-known port number is 110, and IMAP4's well-known port number is 143. LDAP, or Lightweight Data Directory Access Protocol, is a version of your database, your directory database that stores all of your like usernames and password type information, but it's not located on your local area network. It's used by different programs like email as like a directory, so it knows what your username is. and so it can help direct your mail. It uses TCP or UDP, and it uses well-known port number 389. So those are my email and identity management protocols. And then for my remote access protocols, so these are protocols that help me remotely connect to like a server or another computer over the internet to manage it. Start with Telnet. Telnet is an older one that we don't use anymore because it's insecure, but it uses TCP port. It uses TCP for its transport protocol. Its well-known port number is 23. SSH is Telnet's replacement. It again allows you to remotely connect to a server or some other resources and manage it as if you were sitting at it. And it uses TCP as well, and its well-known port number is 22. It's secure, so that's the benefit of it over Telnet. RDP, this is a Microsoft Windows specific protocol, stands for Remote Desktop Protocol. This allows you to, again, remotely control a system, but not only control it from like the command line like SSH and Telnet does. RDP lets you take over the system's monitor, the keyboard and mouse, so that you can actually feel like you're sitting right at the computer because you can even see the screen. But it only works with other Windows-based systems. It can use TCP or UDP as its transport, and it uses well-known port number 3389. A lot of protocols inside of a lot of well-known protocols. Here's some more network operations protocols. You got DHCP. That's our protocol that automatically hands out IP addresses for us. Dynamic host configuration protocol uses UDP as its transport, and it can operate on ports 67 or 68. NetBIOS. This is an old Windows protocol for identifying and allowing communication between devices on a Microsoft Windows-based network. It can operate on UDP or TCP using ports 137 or 139. SNMP, or Simple Network Management Protocol, allows you to have centralized management over a lot of your network monitoring and operations tools. You'll install this as a server role, and it uses UDP ports 161 and 162. And the SLP, or SLIP, or Service Location Protocol, allows computers and other devices to locate services on a local area network without having to be set up in advance. It can use TCP or UDP for transport, and the well-known port number is 427. For file transport, we have FTP, File Transfer Protocol. It has two separate ports, 20 and 21. Both of them operate on TCP. File Transfer Protocol allows you to move files from one location and maybe upload them to a server. You can do it insecurely or securely. So that's why they got two different port numbers they can work with. There's also a form of FTP called TFTP, Trivial File Transfer Protocol, which has less overhead than the standard FTP, which means it's faster. And that's why it uses UDP on port 69 instead of using TCP, because it's worried about speed in that case. Server message block and common internet file system. These are two file sharing protocols that allow you to share files from a server to other devices and printers. It uses TCP port 445. And then AFP, Apple Filing Protocol, is basically the same as SMB or CIFS, except it's proprietary to Apple, so that's what Macs use. And it uses TCP and UDP ports 548. So those are the well-known port numbers that you need to be familiar with for the exam. On on the topic of wireless communications. There's several different wireless protocols that you need to know. All of these were developed by an organization called IEEE, the Institute of Electrical and Electronics Engineers. They gave these different standards the designation 802.11 because that represents the meeting time that they had when they meet together like on a annual basis to come up with these different standards for different types of technology. So the 802.11 standard, regardless of the letter, means Wi-Fi. So anything 802.11, automatically think Wi-Fi. 802.11, the letter, but after that 802.11 just indicates the different type of Wi-Fi that they were recommended and what the specs were for that type of Wi-Fi. So the oldest one there is 802.11a. The max speed on that is 54 megabits per second. The max distance is 115 feet indoors. The frequency it used, as far as like the radio frequency that it transmits on, is 5 gigahertz, and it's not backwards compatible because it was the first one. 802.11b, you see a speed reduction to 11 megabits per second. Still the same maximum indoor range of 115 feet, but they switched the frequency. That's why I got lower speeds. 2.4 gigahertz is a really common frequency. They use that for like not cell phones, but cordless phones use it. Microwaves use that frequency. So a lot of devices use that 2.4 gigahertz frequency. This not backwards compatible with A because of the frequency difference. 802.11g jumps the speed back up to 54 megabits per second, extends the distance indoors to 125 feet, still keeps the 2.4, the popular 2.4 gigahertz bandwidth, but because now it's on the same bandwidth as B, it's backwards compatible. 802.11n jumps it up even higher to 600 megabits per second speed for wireless, extends the indoor range to 230 feet, and is the only type of Wi-Fi that can broadcast on both frequencies, 2.4 or 5 gigahertz. This is why if you have like, let's say you got Comcast in your house or Verizon like I do, my wireless router puts out 2 wireless signals, 2.4 gigahertz one and a 5 gigahertz one. So you'll see you'll see that reflected in the SSIDs that are being broadcast from that router. This one is backwards compatible with all the previous versions of Wi-Fi, A, B, and G. And then the latest and greatest, 802.11ac, jumps way up to 1,300 megabits per second or 1.3 gigabits per second. The maximum indoor range decreases back to 115 feet, and now it exclusively uses the 5 gigahertz bandwidth, and is backwards compatible only with 802.11a and n, the other ones that use 5. In addition to Wi-Fi, there are other forms of wireless communication. They all have one thing in common. They're all using radio frequencies. So Wi-Fi is, even though we think of wireless as like this, like the latest and greatest of networking, wireless has been around for a long time because we've been using radio for a long time. They had radios way back in like the 1920s. So now it's just a different application of those same radio waves. Wi-Fi uses radio waves. Bluetooth uses radio waves. They're just shorter range radio waves. So you can see from the frequencies, 2.4 to 2.485 gigahertz is not as strong as a radio signal, which means it doesn't travel as far. There's several, you can have up to 7 devices linked together with Bluetooth to create a personal area network. And its standard is the 802.15.1 standard. So that's your standard for Bluetooth. RFID is another type of short range radio transmitter. RFID stands for radio frequency identification. It can be passive or active. Passive meaning that the reader itself will pull the information from the device. So let's say I have like a badge. People use this at their offices all the time. Like let's say you work in a secure office, you got the badge into the office. You'll have a card that will have a RFID chip inside of it. And then once you go up to your door, there'll probably be some type of receiver there. You tap your card to the door, and that receiver pulls the information wirelessly from your card to authenticate whether or not you can come in that door, and if you can, then it lets you in. So in that instance, your card is passive. The reader actually has to activate it. But then there are also active RFID devices where it broadcasts its own signal, and it has a range 100 meters. It uses the 125 megahertz to 960 megahertz radio frequency range. So you can see that that's even smaller, because remember, megahertz is smaller than gigahertz. Giga means billion, mega means million. So 1 gigahertz is 1,000 megahertz. So this is less than 1 gigahertz. Okay. And then NFC, or near field communication. This again, another type of wireless. The devices have to be super close. They have to be within 3 centimeters of each other in order to transmit their data. This is when you see like the Apple Pay or Google Pay, where the person has like a payment terminal, and then they can have it pull up their credit card on their phone, and then basically bump their phone to the payment terminal, and it'll transmit the credit card data from their phone to the terminal. That's an example of near field communication. There's a special antenna, a special radio antenna that can produce that signal in certain mobile devices to let you take advantage of that. Zigbee and Z-Wave, these are 2 wireless standards that were created specifically for IoT devices, Internet of Things. So all that non-standard stuff that has network connections, like think of like smart thermostats and smart refrigerators, basically all the smart TVs, anything that's smart and is not a computer, uses Zigbee or Z-Wave as its standard for how it can communicate with other things. The IEEE standard for Zigbee is 802.15.4. It communicates over the 868 megahertz or 2.4 gigahertz range, and it can has a range of up to 20 meters. And you can see how many devices it can support. 65,000 devices at speeds of up to 250 kilobits per second. So pretty slow. But it creates a wireless mesh network inside of your home or whatever. So it's not just your phone talking to that smart device. That smart device can talk to other smart devices that are around it. And then Z-Wave is just another implementation of it. Z-Wave is a proprietary protocol, though. So anytime you see an IEEE standard, that means it's an open protocol. IEEE is a nonprofit. They come up with standards that anybody can use. Any company can take an IEEE standard and use it in their technology. But then you'll have proprietary or company-owned protocols too that some company invented specifically for their technology. So this is the standard for this Z-Wave one. Cellular is another type of wireless we talked about before. The G's in cellular don't stand for gigabits. They stand for generations. So the first generation of cellular communication had these characteristics. It was only for analog calls. Then when 2G came out, it allowed digital voice conference call and caller ID, and it had speeds of 9.6 kilobits per second. When 2.5G generation came out, it then added web support. So then that's when cell phones started to finally be able to get on the internet and browse. And you see the speed jumped up in order to be able to accommodate that 237 kilobits per second. When 3G came out, you had speeds fast enough to support full motion video and streaming music, 2 megabits per second. 4G can support IP version 6 so that it can do voice over IP, gaming, high quality multimedia at 672 megabits per second speeds. With 4G LTE, that gets pushed up even further into the 100 megabits per second, which is significant because 100 megabits per second is the same speed that we call fast. If it was a wired connection, we would call that fast Ethernet. That's the speeds that home networks that plugged in used to have. So with 4G LTE, you can have speeds that used to be reserved for, plugging into your home router. You can get that on a mobile device now. And then with some implementations of LTE, you're pushing it up even to 1 gigabit per second. That's what you might see on a commercial, like a business class wired internet connection. And then 5G is such a big deal because of 5G. It supports download speeds and this of 3 gigabits per second and upload speeds of 1.5 gigabits per second. So that is a huge leap. And with 5G, this could actually, the reason it's so kind of game changing, and you hear so many commercials and stuff about it, is because 5G rivals what you have on your home internet. So you could basically, if with speeds like that, you could replace your home internet with a cellular network connection, and then you'd be able to travel around wherever you want to and have super fast speeds equivalent to what people, like beyond what people used to have on their home wireless networks. So that would make 5G would make, say T-Mobile a competitor to Comcast then as an internet service provider. And monetary, this is off topic, but internet service providers, the more competition there is, the more the price gets driven down. So that could be good for us consumers. All right. In our networks, another way that we can address them is based on architecture, client server, based on management architecture. So there's one architecture called peer-to-peer, where every device on the network is its own like boss, is its own server. Nobody's centrally in charge or centrally managing those devices. Everybody's kind of in charge of their own thing. That's typically not what you're going to see in a corporate environment. Typically, you're going to see what they call a client server architecture, where you have these different clients, these different end user devices, computers that your average user uses. But then you're going to have these servers that act as like a central management and storage location for resources. And that's what you're going to see typically in a corporate environment. But not all servers are created equal. There are servers that do different things. These servers have roles. So a couple of popular roles for servers that they mention here are things like file servers, web servers, and email servers. And each one of those servers is going to have a client too. So file server, we'll start with that one. A file server's job is to serve files. It's a central storage location for files that more than just one person need to get to. Maybe you have a division in your company and y'all have these files that y'all work on together within your division. You can store them up on the server so that everybody can get to them. They won't be sitting on one person's computer. In order to access those files, though, your client computer needs the client software to connect to that server. Same thing with a web server. A web server is going to hold all of the pages for a website. and it's going to serve them up to, people for endpoints to connect to and see that website. In order to see it, you have to have a web client. That web client will be something like a web browser. And then same thing for email. Your email server will collect and store emails. In order for you to retrieve your emails, you need an email client on your system. Or you need a web-based email client. A DHCP server is a server that manages all the IP addresses for your organization. So remember, we said that it had DHCP hands out those IP addresses. And the reason that this is helpful is if you're in a bigger organization where you maybe have hundreds of computers, you don't want to manually try to manage giving out IP addresses to all of those devices. So you create a server that does that automates that job for you, for like probably like 95% of your systems. There are going to be some that you still have to manually assign IP addresses to, but those will be systems or devices whose IP addresses don't change on a regular basis. The majority of the systems in your environment, their IP addresses will change on a regular basis, so you let the DHCP server handle that. DNS server, we mentioned this one too, does the name translation. It can turn Cisco.com into 198.133.219.25, because your computer doesn't really understand Cisco.com, but it does understand IP addresses. It's able to use that address to locate that resource on the internet. DNS makes it possible for us to use the human readable names instead of memorizing a bunch of IP addresses when we're surfing the internet. A print server allows you to centrally manage print jobs. So instead of you sending your print request directly to a printer, instead it'll go to the server. The server will maintain a queue, which is like a line, and it'll help prioritize those print jobs. And then once the printer becomes available, it sends a print job to a printer or maybe even a bank of printers that it manages to print out your job as needed. But that centralized administration is probably the big benefit of the print server. That way you can prioritize one print job over another one. Let's say your CEO wants to print something out at the same time as, the intern in the organization. Maybe you prioritize the CEO's print job over the intern, or maybe the finance people need this report immediately, but then the marketing people are hogging the printer up. I can go on a server and I can prioritize the finance department's print job, even though the marketing department is already printing stuff, and it'll pause what the marketing department is doing and print out the finance department stuff, and then pick back up where it left off with the marketing department's print jobs. Talked about file server already. Here to mention some of those protocols we talked about, though, the file transfer protocols. So you can use those in conjunction with your file server to move files back and forth between server and client. Here's web server, talked about that already. Mail server, talked about that one. Here's an interesting one, authentication server. So the job of a AAA server is to provide those three services: authentication, authorization, and accounting. These are three important services on your network because, one, authentication provides access control. It determines who's allowed to come into your network. So think of your AAA server as like the gatekeeper or the bouncer to your network. User one here, this person on its computer, this remote client, says, I want to get into my corporate network, but I'm working remotely. So I try to connect VPN, and then once I connect VPN, I send my request to connect. That request goes to a AAA router. That AAA router is going to prompt me for a username and password. If I supply a username and password that once I supply that username and password, the router can authenticate me. It can say, okay, yeah, that username exists, and that's the matching password for it. Let me let this user know that they can get in. So let's the user know that they can get into the network. That that user is then able to access. Well, in addition to getting notified that they can get in, that user's credentials are then passed along to a AAA server so that they can actually get access to those remote resources that they need. Once they're in, though, they're not just able to do whatever they want. The reason it's called a AAA server is because it provides also authorization and accounting. Authorization means that um, it's going to give you your set of permissions of what you're allowed to do once you get in, and then accounting is means it's going to keep track of you. It's going to audit you while you're doing things on the system. It's going to keep a log. But you have a server that manages that initial authentication. Um, syslog server. This is a special server that collects your system logs and it stores them in a database. So they'll collect logs from all of the different systems that you might have on your network. So in this example, they have system messages coming from your router, system messages coming from your switch. They're going into the syslog server and they're being stored on a database. That little cylinder represents a database. That way, as an administrator, if you need to troubleshoot something, you can go to the syslog server, look in that database or search that database, and you can find log entries that describe what activities were going on the router and on a switch that can help you with your troubleshoot. All right, basic networking devices. Again, for my folks who have done the IT fundamentals, this should be a really good review for you, but hopefully it'll give you a little bit more insight into some of those components that you were introduced to during the IT fundamentals training. Right. In pretty much all of your modern computers, nowadays you're going to have some type of network interface card, or we call them NIC cards, that allow you basically a way to connect to a network either via wire or wirelessly. So your traditional NIC card is an Ethernet NIC card. It's a special type of adapter card or an expansion card that gives you that port on the back of your computer to plug your Ethernet cable into. You also have wireless NIC cards. So the one in the picture here is meant for a desktop computer. So let's say you have a wireless network in your home and your router is in a place that's not convenient for you to actually run a cable from the router to your computer. One alternative that you can have in order to still be able to use your desktop is to purchase one of these adapter cards, which will add a transceiver. That's that antenna that's on the back. They call it a transceiver because it not only transmits wireless signals, it also receives it. So transmit and receive, transceiver. But then that'll basically give you desktop wireless functionality. Or if you don't feel like cracking open the computer to install an actual adapter card, they have a lot of USB attached ones now. So this is the one at the bottom. That's a USB NIC card, which basically serves as an external wireless NIC. And you can see it has a little antenna built into it. Some of them don't even have that antenna anymore. That just adds to the signal strength. But some of them just look like small little, you could mistake them for like a Bluetooth USB adapter, but it really is adding an external network card to your system so that you can make a device that wasn't meant for wireless able to get on wireless. Besides the devices that allow your endpoints to connect to wireless, you're also going to have a group of tools in networking that we refer to as infrastructure tools. They call them infrastructure because they provide the infrastructure for you to actually communicate through. And there's been, just like everything else in technology, there's been a progression with them. We started out with a tool called a repeater. A repeater is a pretty basic tool. All it does is take a signal and add extra voltage to it. It boosts the signal so that it can continue along its journey. Electrical signals after they travel a certain distance, they degrade. That degradation, they call it latency. So latency is a loss of signal strength over distance. That's why if you ever look at like telephone, if you've ever been driving down a road where they actually still have like above ground telephone poles, you'll notice that there's not just one telephone pole and then miles and miles of road. There's a telephone pole every so often. The reason being is the telephone signals are electrical. So they have to be boosted every so often so that they can continue to travel. Electrical signals in networking are the same way. They need to be boosted every few hundred feet so that the signal strength won't degrade. So these repeaters basically do that. They take a signal in, they give it a bump of power so that it can keep going. So that was the original infrastructure device. They came out with another infrastructure device that was a little bit more useful called a hub. This hub is a multi-port repeater. It takes in an electrical signal and then it repeats that it boosts that signal and repeats it out of all of the other ports that are in the hub. These hubs became the central point of networks. And you can see it in a diagram here, our network diagram. At the center, we got a hub, then we got a bunch of computers and a server and a printer all connected to that hub. So that hub provided a way for not only the signal to be boosted, but connectivity between those different devices so they could communicate with each other. But it's some disadvantages to hubs because, again, they're multi-port repeaters. When a signal goes in, they repeat that same signal out every port, even if the signal wasn't meant for the other devices on those ports. For example, if computer A over here wanted to talk to computer B, it would send its signal into the hub. Instead of the hub just sending a signal directly to computer B, it sends the signals to computers B, C, and D, and the server and the printer. So that creates a bunch of extra network traffic, which is not useful. So we got rid of hubs, but they existed. You might still see them in use for special purposes, but by and large, they've been phased out. But they kind of set the precedent for some future stuff that we'll talk about in a second. Another older infrastructure device is called a bridge. The network bridge serves the same purpose as a physical bridge in the real world. Anytime you can tie this technology to something that you know from your everyday life, the easier it's going to be for you to remember. So when I think of a network bridge, I think of a real bridge. What does a real bridge do? It connects two pieces of land that might be separated by some gap, like a river or a cliff or something. So that's what a network bridge does. It separates two different sections of your network that normally can't talk to each other. And it provides a communication pathway for those two network segments.
Would you say bridges were like the preset to switches and routers?
Yes, that's the next slide. So what the switch does, so the infrastructure device that Nelson just brought up is called a network switch. What the switch does is it takes the functionality of the hub and the bridge and it combines them together. So switches are able to segment networks or break a networks into different parts to control the flow of traffic, but they're also able to act as that central communication device so that all of the devices that plug into it can talk to each other. Essentially, your switch is what creates your local area network. The minute I put a switch in place and then plug all those computers into it, now those computers have a device that they can communicate with through. And just like the hub, the switch is able to take, allow computer A over here to communicate with computer B. But the improvement that a switch has over a hub is that when computer A wants to communicate with computer B, it can make a point-to-point connection. Instead of sending that signal out and repeating it to everybody unnecessarily, it'll send that signal directly to computer B. Now, out of the box, it won't do that. It takes some time for a switch to learn about all of the devices that are plugged into it. So, like right out of the box, it'll function like a hub. But then as that switch begins to learn about those devices that are plugged in, and what it's learning specifically is a certain type of address called a MAC address. MAC stands for Media Access Control. It's the hardware address for the computer. And we have some separate, I got another slide that talks about that a little bit more in depth. But that MAC address, every device that has a network card, a NIC card in your computer has a MAC address and is unique. So you don't have to worry about that MAC address being repeated amongst the devices. So once the switches learn that unique ID, that unique MAC address, it can now do a point-to-point connection between those two devices, so they can just talk to. It could be an A/B conversation, and C doesn't have to be involved. So what you'll see now on modern networks is the hubs have been phased out and replaced by switches, and so have bridges for the most part. They've been phased out and replaced by switches. These switches can either be unmanaged or managed. So that means that I can just out the box again, take a switch, put it in place, plug everything in, and it'll just auto magically work. Or if I want tighter control over that switch, like say in an enterprise environment, the switch has its own operating system. I can go in and I can configure the switch to make traffic flow a certain way, or to group certain devices together so that they talk to each other easier than other devices. So I can actually do some administration through that switch directly. But that's depending on what environment you're putting that switch in. A wireless access point is, you can kind of think of it like a specialized switch. These wireless access points, or WAPs, they call them, provide access to a wireless network. And basically, it's just an extension of your wired network. Even though we're using wireless, ultimately, all wireless has to still connect to some type of wired source. Like think of your home internet, right? You might have wireless internet in your home, but that wireless internet is being generated by that router that Comcast or Verizon or whoever brought to your house, and on the back of that thing there's a cord, right? That's it's plugged in. So essentially, these wireless access points work the same way. They have to tap in to a device like a switch, but then they take that wired signal and then they convert it into a radio signal so it can be broadcast through the air. And that way it extends your network. So now not only wired devices can connect, but your laptops and your mobile devices that rely on Wi-Fi, now they can connect to that same wireless network. Same wired network. They're just doing it wirelessly. Another really important network device is a router. The goal of the router is to provide you a way to get off of your LAN. Routers are considered to be the backbone of the internet because they provide a way for you to use IP, which is the other major addressing scheme in computer networking, internet protocol. Those internet protocols, those IP addresses, let you talk over the internet. And routers provide the gateway for you to get off of your local network onto somebody else's network. So in our example that we're looking at here, you got this small office network over here with its router. This particular type of router is what we refer to as an integrated router. This might be what you have in your home, right? It's not just a router. It's a router that has switch functionality built into it. It's got wireless access point functionality built into it. Think of it like an all-in-one router, because you can see how it's communicating in a bunch of different ways for different devices. But at its core, too, it's still a router. That means it has the ability to send signals off of the LAN and out through the internet. That integrated router is then communicating with this data center, which has a traditional router, antennas on it. That traditional router, in order for it to send its signals to these servers, has to go through a traditional switch. This kind of brings up an interesting point, too. On your smaller networks, your home networks, your small office networks, the acronym that you might see for that is SOHO, small office, home office. On your SOHO networks, you'll typically have these integrated devices. You won't have just a router sitting by itself and a dedicated switch, because you don't need all that. You only got like a couple of devices on your network. Whereas in an enterprise environment, you're more likely to see those devices as standalone, dedicated devices because they'll be more powerful and they'll be able to handle, you know, bigger numbers of um, endpoints connected to them. So that's why in the data center, in this corporate environment, we have a dedicated router and a dedicated switch to support those servers. Firewalls, another tool you might see deployed on networks. This is a security tool. The purpose of a firewall is to act as a filter. It blocks traffic either coming in or leaving out of your network. In this graphic, they're showing firewall functionality. Remember we said the integrated router can have a bunch of functions kind of all packed into that one device. Well, this integrated router not only is a router, not only acts as a switch, but it has a software-based firewall built into it that can filter certain types of traffic based on different rules that you create. On firewalls, you create what's called an access control list, ACL. The goal of the access control list, as the name implies, is to control access to the internal network. That's your protected network inside your home or inside of your company. And you're protecting it from the outside world, from the internet, because there's no rules regulating the internet. The internet's the Wild West. You don't want everything on the internet coming into your internal network. Just like you don't want everything out there on the streets coming inside your house. So you put a door there with locks and security cameras and all that stuff to prevent that stuff from coming inside. You do the same thing on your networks. Firewalls are one of those barriers to protect your internal network from the external world. And you set rules to filter that traffic coming in or leaving out. So you might set a rule based on IP addresses. You might set a rule based on certain sites, but there's different types of rules that you can set. But in this instance, all that functionality is software-based. There are also hardware-based firewalls too. So in a corporate environment, you probably will have a dedicated firewall appliance that does that filtering for you. And you can, like I said, either deny or allow certain types of traffic. Another security device that you might see or functionality that you might see built into an integrated router is an IDS or IPS. IDS stands for Intrusion Detection System, and IPS is Intrusion Prevention System. They both essentially had the same function. They allow you to monitor the network traffic on a network at large or on an individual host, like an individual device, like a server on the network. Because the reason it's able to do that is because they're hardware based IDSs and IPSs. We call them NIDs and HIPs, NIDs and NIPs. So Network Intrusion Detection System or Network Intrusion Prevention System. And they are deployed on the network, and they actually monitor the traffic as it flows through the network. With the NIDs, when it suspects, and here's an example here, when it sees some suspicious activity occur on the network, it basically raises a red flag. It sounds an alarm. It says, hey, administrator, I need you to check something out. I'm going to send you an email alert to let you know something went wrong. But that's all it does. It just notifies you that maybe you need to go take a look at something. The IPS is a little bit more advanced. When it detects an issue on the network, based on rules that you've created, it can take proactive action without any further human actions needed. So it detects the issue and it automatically springs into action and it does something to stop whatever that intrusion is. So the IPSs are preferable. The IDSs are still around though, because they can sound the alarm. Those can be deployed on networks or on hosts. If they're host-based, they're going to be software. It'll be a program that you install on a server or on a client device. But they still do the same thing. When that network traffic hits that specific computer or server, it'll either, if it's an IDS, a HIDS, host-based IDS, it'll sound the alarm, send you an email, say, hey, check on this server because something suspicious is being detected. If it's a HIPS, a host-based intrusion prevention system, it'll still trigger an email, probably notify you, but it'll say, I detected some suspicious activity, and this is what I did. Now go check on it. So again, the IPSs are preferable because they're proactive, but the IDSs are less expensive, and they still at least give you a heads up. You also have what they call universal threat management devices. These are, again, all-in-ones. Typically, your all-in-ones are marketed toward small office, home office environments where, again, you might not have a budget, or you might not just have the capacity to have individual devices to do all of this stuff. So instead, you buy this all-in-one device that can do everything. So some common things that a UTM will handle are things like firewall functionality, IDS and IPS. They might have software that can do spyware detection or detect different types of denial of service attacks. Might do email filtering or proxying, network access control, or even provide VPN services for your overall network. Endpoint management server. This is a newer type of technology that provides a really critical service to your network, because endpoints are actually the place where you get attacked the most. You would think that, when a hacker tries to hack, they're going to go after the servers because that's where all the information is. Yeah, they ultimately want to get the servers, but usually when an attack happens, the way they get in is through somebody's, some user's laptop or desktop computer, because one, there are more of them than there are servers. You might have, 100 servers on your network, but you might have 1,000, desktop and laptops on your network. So it's just a bigger target to go after. Plus, the people using the servers are typically highly trained IT professionals. So they're doing backups, they're doing antivirus scans on stuff on a regular basis. Your end users, they're not trained so well, right? They might not be, they're probably not IT people. They might be an accountant or, HR person. So their machine is more likely to be more vulnerable than a server is. So it's easier for an attacker to go after that endpoint and then make their way to the server than to go after those higher value targets outright. So because of that, endpoint management is kind of a big deal, because traditionally you had the only way you could manage an endpoint, like a desktop or a laptop, was to go to that person's laptop or desktop and do stuff to it directly. But now with endpoint management servers, you can have centralized management over all of the desktop and laptop and servers and tablets, everything via one pane of glass. One pane of glass means I go into one computer program and I can see and manage all those devices. So an endpoint management server would be the central management point that's providing you with that single pane of glass. And then you would probably install what they call client applications on all your devices so that they can report in to that central management point. On your networks, you might encounter some legacy or embedded devices. Legacy just means old. It's probably technology that's not supported anymore. Like the manufacturer doesn't, whoever made the technology doesn't even make updates and stuff for it anymore. They're like, we came out with a newer version. If you still want to stay on that one, you can stay on that old version or old technology at your own risk, because we have a newer one that we think you should use. But in some cases, companies are like, oh, we've been using this software, we rely on this, it's mission critical, we don't want to change it. Sometimes it's not legacy hardware, sometimes it's legacy software. Might be software that they had custom built, and they don't want to change it because they'd have to pay for somebody to rebuild it. So anything, but just remember that term legacy just means it's old, it's no longer supported. You also have embedded systems, which means that that software is a part of the physical device. So one example of that is thin client computers. We talked about thin client computers earlier in chapter 5. But these thin client computers a lot of times have their operating system on a chip, on a microchip that's actually embedded in the motherboard. And that microchip can't be overwritten. So basically, the only way to upgrade the operating system would be to get a whole new microcomputer. Um, so with those, again, they tend to be legacy as well, because when their operating system goes out of date, the only way to get a new one would be to get a whole new device. But if you want to hold on to that device, you got to just deal with that legacy operating system. These you'll find them especially on bigger corporate networks, and because they might become mission critical, even though they're older, they might be doing really important things for the company. So you just kind of got to watch out for them, because they can introduce a security risk because they're not being updated. They're not protected against modern viruses and things like that. From a network connectivity perspective, you'll see these things if you go into a network wiring closet. They're called patch panels. When you go into like a building, right? You might go into like an office building or something like that. And in offices, you'll probably see little jacks on the wall for people to plug their not only phones, but plug their internet cables into those wall jacks. So they plug into those wall jacks, but what happens on the other side of that jack? Well, on the other side of that wall jack that you're plugging that cable into, there's wires running up through the walls, through the ceilings, all around the building, but they ultimately end up at some closet or some room. That in that closet or that room, you're going to have these racks. These racks will allow the other ends of those wires to be punched into a patch panel. The patch panels will then give you another outlet, if you will, a jack, for you to plug a patch cable into, and then those patch cables ultimately plug into a switch. Because remember, we said a switch is necessary in order to build a local area network. So in that data center, if it's a big, if it's a big company or a big building, like the one here, you see there's tons of cables, right? So that means there's tons of rooms in this building that all have these network outlets, and all those cables are running into this one place, getting patched here, and then all these patches are then plugging into a series of switches so they can build their local area network. Again, you'll find these in a wiring closet. Sometimes you'll find them inside of a data center. But this might be a place that you might have to look in patch panels in order to troubleshoot certain connectivity issues. A special type of switch that you might see in one of those wiring closets is called a power over Ethernet switch. Typically, switches only provide data connectivity, right? So you can talk on your local area network. But there are going to be some instances where you have devices that need to communicate through the switch that aren't able to have their own external power source. Some examples of that are wireless access points, or IP cameras, or even phones. Those devices might be placed in areas that is not convenient for you to have a network connection and an outlet to plug in the camera. All right, what if it's sitting up on a pole or sitting up in the ceiling or something? You don't have no outlet there to plug that camera in. So what power over Ethernet does, since it has electricity running through those cords anyway, it gives an extra bump of electricity to the device that's plugged in on the other end. So not only does that Ethernet cable provide a data pathway to communicate through, it also provides a jolt of electricity to power the device. That's why if you ever seen a voice over IP phone, there's usually just one cable plugged into it, the Ethernet cable. And that Ethernet cable is not only giving you your pathway for your data communication, for your voice communication, but it's also powering the phone as well. You have another device that goes along with that you might see is a power injector. The power injector is going to be put onto devices that need that PoE functionality, but if you don't have a PoE switch like this one here, maybe it's only a couple of devices that need PoE. So instead of going out and buying a 40-port PoE switch, Maybe I keep my regular switch and I just buy a power injector. And that power injector gives me 1 or 2 ports that can have that PoE functionality. It adds, the injector adds that extra boost of electricity that's needed to power the device that's plugged in on the other end. Now, this is a pretty cool function, pretty cool technology here. This is called EOP, Ethernet over Power, or power line networking. What this device basically does is it converts, or not converts, it allows the electrical wiring in your house to be used as network cabling. So the reason this is cool is, let's say you're in an older building that was made before networking was a thing. Like maybe you got an old house, you purchased an old house from like the 70s or the 80s, but before, or even modern houses. I mean, most people's houses don't have network drops built into them. So instead of having, wires all over the place, you're trying to run network cables. Maybe you have that desktop computer that we were talking about earlier, and you don't want to make it wireless. You want to take advantage of the wired network speed. One solution would be to purchase an Ethernet over power device. And what it does is it lets you plug into a nearby power outlet, and it converts that power outlet into an Ethernet drop. And then you go to your router and you'll plug in another PoE switch, and then you'll run a network cable into that router. And through the walls, it'll use the electrical wiring that already exists in your home as network wires, so that it can carry not only power, but carry a data signal through your home's electrical system. Um, on the kind of cutting edge of the newer types of networking technology, we have what they call cloud-based network controllers. So with most of your networking, like traditional network controllers, those devices had to be located inside your data center or inside your networking closet, physically on your site. But with a cloud-based network controller, you could have, multiple networking devices, switches, access points, all scattered around all over the place, and you can control them, centrally manage them via an internet connection um, through the cloud. So one example of this, the one they have pictured here, is a Cisco technology called Meraki. That's their cloud-based wireless access points. They have security appliances. They even have cloud-based routers. So it's a pretty cool technology to learn. Network cables. We talked about some network cables earlier in the section. We'll do a recap, but the tools that you need in order to make these network cables are going to be wire cutters to actually, cut your different types of network wires. That's these snipping looking tools here. A wire stripper, that's this tool, this other red handled tool. This actually helps you strip the outer sheathing. Most of your, all of your network wires are going to have some type of outer coating to protect the internal wires. And if you're going to be making your own custom runs of these wires, you got to strip that outer coat off in order to get to the inner part to make your connections. So they have a tool called a wire stripper that helps with that. The crimper, this is used specifically for Ethernet or telephone cable. And this is the tool you use to actually put those ends, those RJ, those registered jacks onto the ends. So this particular crimper can do RJ45s. That's the connector that Ethernet cable uses. And the crimper presses that those connectors down and makes them bite into the wire, so that connector doesn't, it makes connectivity, makes contact, and so it won't fall off, so you can plug it in. And then the punch down tool. This is the tool that you use for the other side of an Ethernet connection. So if I'm making like an Ethernet wall jack, I'm going to not use a male RJ45, the one that looks like a little connector clip. I'm going to use a female RJ45. That's the one that acts as the receptacle for the plug to plug into. And I'm going to still use an Ethernet, the same type of wiring, except now I'm going to use this punch down tool to punch those wires into place to get my wall jack ready for installation. Additional tools that you might use in your having your networking kit, a multimeter. This is a tool that we use to measure the different qualities of electricity, the ohms, the volts, the wattage. So this comes in handy when measuring, to see if an outlet works or if electrical current is running through certain wires. So that's a handy tool. A tone generator. Sometimes they call it a fox and hound. This tool is used to map different wire segments. So if I'm trying to determine if a wire, for like long wire spans that might run through a wall, I'm trying to determine where that wire starts and where it ends in the network closet, I can use this tone generator or fox and a hound in order to send a signal through the wire. And then when I touch the other end of that tone generator to certain wires, when I touch it to the one that's connected to the other end, the generator, it'll create an audible sound like a buzz. And then that's how I can locate the right wire I need to work on. A loop back adapter, that's this little plug right here, sends an electrical signal through a network card and then loops it back into your computer. It's a way of externally testing certain types of adapter cards. And there's loop back adapters for all types of stuff. Probably the most common one you'll see, though, is a loop back adapter to test your network card. Cable testers, that's this tool here. This one is used to test Ethernet cable that you've created. So if I make or there might be, there's some for fiber optic, there's some for also for coaxial cable, but this is an Ethernet one. So if I'm making my own custom runs of Ethernet cable and I want to make sure that I wired it correctly, I can plug each end into one of the halves of these cable testers. It'll send a signal through and it'll let me know what wires are receiving signals on the other end. So I can see if the wire has been wired correctly. And the last one here is a wire analyzer. The laptop itself isn't really the analyzer. This extra antenna and the software that you're running on that laptop act as the analyzer. Sometimes you don't even need that extra antenna. You can use the internal antenna that's already built into your laptop. It's mainly the software. That software is able to take a survey of the wireless signals that are present inside of your business, your building, and make a map. And we call them a heat map. The heat map will show you where the wireless signal is strong and where it's weak. And that way you can go around to the different, wireless routers or wireless access points, and you can tune them to make sure that they have the proper signal strength and coverage. To connect your network devices in a wired fashion, there's 3 types of cabling that we typically use. First one's called twisted pair, then we have coaxial, and then we have fiber optic. Your coaxial cable is you're probably most familiar with seeing it in cable television, those thick black wires that they use to connect your cable TV systems. That's one form of coaxial. The way that they're made is they have a single copper conductor. So they're sending, electrical signals, but they're sending it through this one thick copper wire. Outside of that wire is coated with a plastic coating for insulation. And then there's a braided copper shielding over top of it, and then it has an outer jacket. So you can see that this copper wire has a lot of shielding on top of it. This makes it good for running outdoors or through environments that might have a lot of potential interference. So that's why you can run a coaxial cable from a telephone pole to somebody's house to give them cable television, because they're pretty they're weatherproof, and they can handle being outdoors and dealing with the all of the other competing signals. When it comes to installing them, though, they're harder to install. The wire itself is more expensive, and it's harder to troubleshoot them because it's got that single copper core. So you won't really see them used for like general networking, but you'll see this type of cable used in specific purposes, like for your cable television or like CCTV, closed circuit television camera, for security systems. The connectors that they use, so that this is the actual cable is called coaxial, but the connectors, the end connectors that they use are BNC connectors. That's an older connector that has a lock and twist mechanism. you push the connector onto a nub, and then you twist it and it locks in place. You have this N-type connector, which actually gives you the little screw on nub at the end of the wire, and then you have an F-type connector, which screws onto that little nub. So this is probably the one you are most familiar with, because like on your cable television, it has an F-type connector that you screw on to the back of your cable box. Twisted pair cable. This is the most common type of cable that you'll see in networking, both in homes and in an enterprise environment. There's two types of twisted pair: UTP, which is unshielded twisted pair, and STP, which is shielded twisted pair. They both have the same wire makeup. They have four pairs of wires inside of them that are twisted. Each 8 wires in all, but the pairs are twisted together. The reason for the twist is to provide some type of protection against interference. But some of those wires can also, after you untwist them, they can be used to generate signal. In unshielded twisted pair, the only protection are those twisted wires. But other than that, that type of wire only has a plastic outer coating, outer jacket. That you can see that here, that blue outer jacket there. This means that this wire is pretty susceptible to interference. Mainly two types of interference: electromagnetic, or EMI, and then radio frequency or wireless interference, RFI, radio frequency interference. If you have to run this type of cable, twisted pair cable, in an environment that has a lot of EMI and RFI, then you might want to pay a little bit of extra money and get STP, shielded twisted pair. The shielded twisted pair cable still has the wire twists in it, but then each pair of wires has a foil coating over top of it, and then over top of all of those foil coatings, there's a braided foil sheath, and then you have your outer jacket. So similar to the coaxial, where you have multiple layers of shielding over top of your cable, that shielded twisted pair implements that, and that provides some protection against EMI and RFI, but still not as good as the coaxial. Like, you still wouldn't run this outside, but at least inside you can have some protection against that type of interference. Even though this STP is more, is more protected, you'll still see that UTP is the most commonly used form of twisted pair cable, because most your like office environments and stuff, they don't have a whole bunch of electromagnetic interference. So this is suitable for that. There are different, if we think about, again, things like technology as having selling points, or basically those like key characteristics that set it apart from other types of technology. One of the selling points for twisted pair cable is its speed. So there's going to be different types of twisted pair cable, and they're ranked by their different speeds. We've had way down to category 1 or Cat 1 cable, but that stuff's not used anymore. Probably the oldest version that's still in use is Cat 3. Cat 3 cable is telephone wire. But for network communication, the oldest type of category cable you're going to use is Cat 5. So Cat 5 UTP has a speed rating of 100 megabits per second. Cat 5E or Cat 5 Enhanced can handle speeds of up to 1 gigabit per second, and then Cat 6 can handle speeds of up to 10 gigs per second. They have 1 gig listed here, but at a higher frequency. But you can read the details to see some of the other benefits that Cat 6 has. So if you are in an office environment and you want to take full advantage of your corporate network connectivity, which probably will be a gig per second, you got to have the right wire. If you're using Cat 5, that wire itself is going to limit how fast your network can run. You probably need to upgrade your wiring in order to take advantage of those faster speeds. When you're creating this twisted pair cabling, there's 2 wiring schemes that you can choose from: the T568A or T568B. And this is the the pattern basically that you have to put those wires in order for them to communicate. Now, based on how you wire each end of that cable, you'll create different types of cable. The most standard type of network cable is called straight through because you wire both ends of the cable exactly the same. You'll choose one of these standards, the A standard or the B standard, and you'll put the wires in that pattern on both ends. And then it allows the data signal to run straight through the cable. If you're trying to connect together two devices that are of the same type, like I'm saying, let's say for example, you want to connect two routers directly together. Well, a straight through cable won't work because those two devices are trying to communicate the same way. They have to have their signals flipped in order to do that. So you would use what they call a rollover cable, crossover cable. So with a crossover cable, you'll have the wiring scheme be A on one side and B on the other side. So just kind of keep that in mind. The way you wire it makes different types of cables. The most common type is called a straight through. Here's our third type of cable. It's called fiber optic. This is the most advanced one. Fiber optic cable is the only network cable that doesn't use electricity. Instead, it uses light. So it actually moves your data at the speed of light. It's able to do that by sending a laser signal through a fiber glass core. So similar to the way that the coaxial was set up, there's a single core in the center of your cable. That fiberglass core is where the transmission of the signal happens. And then outside of that fiberglass core, you got a bunch of different shieldings just to trap that light in there. It's not really it's protecting it from the outside world, but it's mainly so that there won't be any ambient light leaking into the core that can mess up the signal that's traveling, the laser signal that's traveling through it. Fiber optic is the only type of cable that's 100% protected against electromagnetic interference and radio frequency interference because it doesn't use electricity. It uses light. There's two different implementations of fiber. You have what they call a single mode fiber and multi-mode fiber. In single mode fiber, you'll have a smaller core, like that fiberglass core is smaller, but when you send your light signal down it, you send the light signal straight down the center of the core. So basically, you're only allowing one signal to travel through that core at a time. Because only one signal is traveling straight through that core, these wires can run for super long distances, like states long, like hundreds of miles type long distances. So if you need to make a run, if you have special training to do fiber optic cabling, and you're trying to make long expanses of cabling, that's the mode that you're going to use. You're going to use single mode fiber because it can travel further. If you are trying to get multiple signals at a high speed through a single fiber optic cable, then you'll use multi-mode fiber. Multi-mode fiber, instead of sending a signal straight down the core, it'll send multiple signals through the same core, but it'll angle them. Notice the diagram here. You see we got like two signals going through this core, but they're at different angles. And as that light signal hits the sides of the core, it bounces. It bounces back and forth down the core, but it bounces in a different angle than the other signal. That way they can coexist. They don't overlap each other. They're bouncing at different angles until they reach the device that they're trying to communicate with. All that bouncing around causes them to lose energy, so they can't travel as far, but you still get the advantage of them moving at the near the speed of light. Plus, you can get multiple signals down the core at the same time, and it's cheaper than a single mode fiber. The connectors on the ends of those fiber optic cables will be one of these four. They have what they call the straight tip connector or the ST connector. They have the Lucient connector, or the LC connector. This was created by a company called Lucent Technologies. And then they have the SC connector or the square connector. And you can see by the square shape, that's where it gets its name from. And then you have the duplex multi-mode LC connector. So this is the same type of LC connector, but it has two cores on it. And it's a smaller connector. All right, so that's it for chapter 5. Any questions? All right, let's keep it rolling there. Set the timer. Let's hop right into chapter